Basic transformations. Translation, rotation, scaling. Transformations for complex movements. Advanced transformations perspective. Definition of transformation in graphics. Importance in computer graphics and animation. In graphics, transformations refer to the processes of altering the position, orientation, size, or shape of objects. These changes typically applied to points, lines, or polygons in the coordinate system. There are several types of transformation commonly used in computer graphics. Translation: moving an object from one position to another by adding a constant offset to its coordinates. Number 2. Rotation: changing the orientation of an object around a specified point of axis. Scaling: resizing an object by multiplying its coordinates by a scaling factor along each axis. Shearing: skewing the shape of an object along one or more axes. Reflection: mirroring an object across a specified line or plane. Projection: mapping 3D objects onto to the surface, often used in rendering to create perspective effects. Transformations are fundamental in computer graphics and animation to several reasons. Manipulation of objects. Transformation allow designer to move, rotate, scale, and deform objects to achieve desired visual effects. Animation. By applying transformation over time, animation can be created. For example, a series of translation transformations can simulate the movement of an object, while rotation transformation can create spinning or tumbling effects. Scene composition. Transformation are essential for arranging objects within a scene, enabling designers to position objects relative to each other in the viewer's perspective. Camera movement. In 3D graphics, transformations are used to simulate camera movements, allowing the viewer to explore virtual environments from different perspectives. Efficiency. Transformations can optimize rendering by reducing the amount of data that needs to be processed. For example, instead of storing multiple copies of an object in different positions, a single object can be transformed to appear in various locations within the scene. Basic transformations. Translation. Definition and explanation. Example demonstrating translation in 2D and 3D space. Rotation. Explanation of rotation transformation. Example illustrating rotation in 2D and 3D space. Scaling. Definition and significance. Example showing scaling in 2D and 3D space. Translation. Translation involves transforming an object from one coordinate system to another. It typically includes operations like moving, rotating, and scaling the object while preserving its shape and properties. Example, demonstrating translation in 2D. Imagine a square with vertices at 1, 1, 1, 2, or 2, 2, and 2, 1. Translating this square by 2, 3 would result in a new square with vertices 3, 4, 3, 5, 4, 5, and 4, 4. Example, demonstrating translation in 3D. Consider a cube with vertices at 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 2, 1, 1, 2, 1, 2, 2, 2, 1, and 2, 2, 2. Translating this cube by 2, 3, 1 will result in a new cube with all vertices shifted by 2, 3, 1. Rotation. Rotation transforms an object by rotating it around a specified point or axis. It changes to orientation of the object while preserving its size and shape. Example, illustrating rotation in 2D. Consider, consider the same square as before. Rotating it by 90 degrees clockwise around the origin would result in a new square with vertices negative 1, 1, negative 1, 2, negative 2, 2, and 2, negative 2, 1. Example illustrating rotation in 3D. Imagine the cube from earlier. Rotating it by 90 degrees clockwise around the y-axis would result in a new cube with vertices shifted accordingly. Scaling. Scaling involves resizing an object by multiplying its coordinates by a scaling factor. It can either enlarge a scale factor 1 or shrink scale factor the object. Example showing scaling in 2D. Using the initial square, scaling it by factor of 2 would result in a new square with vertices at 2, 2, 2, 4, 4, 4, and 4, 2. Example showing scaling in 3D, applying the same scaling factor to the cube would enlarge or shrink in all three dimensions, depending on the scale factor used. Complex movements. Introduction to complex movements. Combination of basic transformations. Example, robot arm movement. Sequential application of translation, rotation, and scaling. Visualization through animation or diagram. Imagine a robotic arm in a factory setting. It needs to perform various tasks such as picking up objects, assembling parts, or moving along a specified path. Achieving these actions efficiently requires orchestrating a sequence of basic transformations. Number 1. Translation. This involves moving an object from one location to another along a straight line in the context of a robot arm. Translation might involve extending or retracting certain segments of the arm to reach a specific position. Rotation. Rotation entails turning an object around a fixed point. In the case of the robot arm, rotation could be used to adjust the angle of joints, allowing the arm of orient itself correctly to grasp or manipulate objects. Scaling. Scaling modifies the size of an object, either increasing or decreasing its dimensions. Although less common in the text of a robot arm, scaling might be necessary for tasks that involve handling objects different sizes. Combining these transformations allows for complex movements. For instance, to pick up an object from a conveyor belt and place it on nearby shelf. The robot arm might perform the following sequence. Number 1. Translate. Move the arm horizontally along the conveyor belt to align with the target object. Number 2. Rotate. Adjust the orientation of the gripper to approach the object from the correct angle. Translate. Move vertically to lower the gripper and grasp the object securely. Translate. Lift the object and move it to the desired location on the shelf. Rotate. Orient the gripper appropriately to place the object down gently. Visualizing. These moments can be done through animation or diagrams. Animation provides a dynamic representation showing how the arm transitions between different configurations over time. Advanced transformations. Perspective transformation, definition and purpose, application in creating 3D effects in 2D graphics. Example demonstrating perspective transformation. Perspective transformation is a mathematical process used in computer graphics to simulate the effect of viewing objects in three-dimensional space from a specific vantage point. In the context of creating 3D effects in 2D graphics, perspective transformation involves transforming the coordinates of points in a two-dimensional image to simulate the distortion that occurs when viewing objects from a particular perspective. One common application, perspective transformation, in creating realistic-looking 3D scenes in computer-generated imagery, video games, and virtual reality environments. An example perspective transformation can be seen in the rendering of a simple cube in a 2D image. Imagine, you have a 2D image of a cityscape with buildings of various heights. By applying perspective transformation, you can make the buildings closer to the viewer appear larger and more detailed, while those farther away appear smaller and less detailed, creating a sense of depth and distance.